Hello, I welcome you all. The problem reads draw the shear and the moment diagrams for the beam. This problem is coming from the Engineering Mechanics Statics textbook, 13th edition by R.C. Hibbeler. So to start the problem, we are going to draw the beam. I'll draw it there, and then we have a loading, which is something like so. Right. Okay, something like so. And then so. There we go. Of course, this is a triangular distributed load whose maximum intensity at that point is 50 pounds per feet. And then we have a moment, couple moment there of 200 pounds feet. And then, of course, here this point is A, this point is B, and this very point here is C. So at A we have a hinge with respect to reaction forces AY and AX, and then we have a roller at B. This is going to be BY. And the dimensions are as follows: A to B to C, A to B to C, like so. This is 9 feet and this is 4 feet. Great. So we have an equivalent force from this triangular distributed load, and the magnitude of this force is this triangle, so it's just the area, so it's half times 50 times 9, so this becomes 0.5 times 50 times 9, so this is 225 pounds. And then its location from A is going to be equal to 2/3 of 9, which is equal to 6 feet, right? Great. So now let's find the support reaction, summation of moments about point A equal to 0 and clockwise in our reference. What do we have? We have a minus moment 225 by 6. Then we have a minus moment, okay, clockwise, which is a 200. Then we have plus by by 9 equal to 0. Therefore our by is going to be equal to, okay, let's work out this one. 225, of course, minus 225, right? Minus 225 by 6 minus 200, okay, then divided by 9, we get a 172.22 pounds. We repeat this: 225 by 6 minus 200 divided by 9, 172.22. Okay, so summation of forces in the y direction. What do we have? We have AY plus BY minus 225 equal to 0. Therefore, since we already have what BY is, it's just here. AY is just going to be equal to, so we have 172.22 minus 225. So this gives us a 52.78 pounds. So then we have summation of forces in the x direction equal to 0. Of course, AX is equal to 0 because we don't have any loading in that direction. AY is 52.78 and BY is 172.22 pounds. AX is 0. So let's get rid of this so that we prepare to draw the shear and the moment diagram. So let's draw, let's prepare the space where we're going to be drawing the shear and moment diagrams, like so. All right, so there we go. This is the shear force diagram, and this is the bending moment diagram. Okay, like so. This is 0, plus and minus. Right, now let's do the plots for the shear force diagram and the bending moment diagram. Okay, so at A we expect a value of 52, a positive value, shear value of 52.7. So let's say maybe it goes up to somewhere there, up to there. All right, great. Okay, we are not going to do the shearing, the sectioning method where we section. Okay, instead we're just going to use the differential equations that relates load, shear, and moment. We have the dv dx, okay, which is equal to minus distributed load, and dm dx, which is just equal to the shear. So we have indicated our first shear at A, which is a positive value going up. Okay, this is a 52.78 pounds, and then we are going to have another value at B, but between A and B we have this triangular distributed load, and we know that this load is negative and increasing, and if this is the case, then our slope for the shear will also be negative increasing, right? So let's find the value. Okay, we know that at A we have that value that we just indicated, a value of 52.78. okay, and then minus this negative value that is distributed in between here. So we have a half. We need to find an equivalent force times 50, which is the height, times the base, which is the length, 9. Okay, if we did the subtraction, 52.78 minus half times 50 times 9, this gives us a minus 172. Okay, minus 172 minus 172.22 pounds. Right, so it's going to be somewhere, let me indicate it. Okay, so somewhere here, let's say it is somewhere here. All right, and this value is 172 minus 0.22 pounds. All right, and we've been told, or we know, that shear itself is negative increasing because our load is negative increasing, our shear slope. So negative slope and increasing, of course it has to go like this. Okay, let me draw it properly. All right, I'll just move that point a little bit down. Okay, up to there. All right, so this is the value. That's the value for shear. Okay, so there we go. So we need to find this value here. We need to find this value here. This value here. We need to find the length to that value. At this value, our shear is equal to 0. Right, it's equal to 0. So we need to find the position, the location, right? So for us to find that, we need an equation for shear, so that we integrate it, I mean, we not integrate it, we equate it to 0. Right. This curve that governs the shear is a polynomial of degree 2 because our loading is a polynomial of degree 1. Therefore, shear will be a polynomial of degree plus 1, right? So this one is plus 1, while moment it will be plus 2 in that order, right? Okay, so this one becomes quadratic shear, while the other one for moment it will be polynomial of degree 3. Okay, so now we can find the shear equation either by sectioning here. You section this member and you do all those calculations if you want to. Yes, that's one method. Then another method would be just be direct. This is what I want to do. We know that the equation that governs our load is equal to the gradient. We know gradient is change in y divided by change in x. So we have a 50 change in y divided by 9 change in x times x. All right. And therefore our equivalent force at a distance x will be just half times 50 divided by 9 times x, which becomes x squared. All right. So for us to find that equation, we'll say V, which is shear, is equal to the initial shear at A, which is 52.78, then minus half times 50 divided by 9, okay, x squared. And shear at this point where the curve cuts the x-axis is equal to 0, therefore we equate this equal to 0. And then we make x subject to the formula, it becomes equal to 52 point, because we want to find the value of x. 52 divided by 50 divided by 18, right? And this to the power half. So if we did so, 52.78 divided by 50 divided by 18, okay, so what we find is a 4.36. so this is the value, say 4.36 feet. So the shear here is positive, our shear there is negative. So we need that value because we are going to use it when finding the moment, maximum moment. So we need to use it during the integration. I hope this is clear. Okay, so I'll need to leave this equation because we'll come and use it later on, this equation for shear. Alright, so this is the equation that governs the shear throughout up to the very end there, because if you plugged in the same equation, if you said V at x is equal to 6, we should be able to find 1 minus 172. Okay, it's the same one that you'd find if you did the sectioning. Okay, we just did it in a quick way. Right, this is shear when x is equal to 9, not 6. Sorry, when x is equal to 9. Okay, we're just testing this equation when x is equal to 9. Okay. 52.78 minus 0.5 times 15 divided by 9 times 9 squared. So we have exactly 172.22, which is this value here. Alright. Okay, so now we have that value there. So what we need to do now is to draw the moment diagram, and for us to draw the moment diagram, we need to relate shear force to the slope of the moment. So then we know that shear in this region, the region where it is positive, but decreasing, right? Okay, from 0 to 4.36. Therefore, the slope for the moment, we expect it also to be positive, but also decreasing, right? At A, you don't expect any moment because this hinge does not resist moment, therefore, and it does not transfer any moment, therefore we don't expect any moment at A. Okay, a moment is going to be 0. Right, so a slope that is positive and yet decreasing is going to be something like this, right? Yeah, it may not have been very perfect, but something like that. Okay, so this is our value here. This is our value. Okay, and then for us to find this value, I mean this maximum value, we need to do the integration very quickly. So we'll say maximum moment is that's a maximum moment, right? Is equal to integral from 0 to 4.36 of shear, which is we have minus 50, I multiply that in advance, 18 x squared plus 52.78. Okay, so if we did the integration there, this becomes 50x cubed divided by 3 by 18 is a 54, right? 3 by 18, yes. And then plus 52.78x. And our integration constant is from 0 to 4.36. Therefore, if we plugged in that value in there, this is what we expect. We want to find that maximum moment times 4.36 cubed plus 52.78 times 4.36. So the value we are finding is a 153.38 pounds feet. So this is the value here, which will indicate 153.38 pounds feet. Alright, so that's a moment there at that point. That is the moment. So now let me just wrap this. I'll need to use this again. So now we'll need to move to B. For us to move to B, we need to find the moment at B. Okay, so we need to find the moment at B by finding the moment from A. Of course, we need to from A to B, right? So we already have the moment at A, and it's either we add it or subtract it depending on the sign, and of course it will be negative, so it will be subtracted. So let's find it so that we subtract it from this value 153.38. So now the integration constants, we are starting at 4.36 to 9, so the constants will change here. So at the bottom we'll have 3.36 and then there 9. So if we did that, it will just be equal to the same 54 x cubed plus 52.78x, that is 4.36 to 9. And then let's see what we find. Do the subtraction. So I'll feed everything. Minus 50 divided by 54 times 9 cubed plus 52 point. Let me check this one. Okay, that's fine. 52.78 times 9 close brackets minus 50 divided by 54 times 4.36 cubed, okay, plus 52.78 times 4.36. Alright, so we are finding a value of minus 353.36. Okay, so for us to find the final value there at B, so moment at B will be equal to moment at T, the maximum moment, which is 153.38, and this one is negative, so minus 353.36. So therefore this gives us let me just do that, gives us a minus 199.98, which is just equal to 200 minus 200. So we are going to expect a 200 somewhere. Let's say 200 is somewhere here. All right, let's say 200 is somewhere here. So we're going to have a sharp 4. We'll have a sharp 4. Okay, maybe I draw this properly now. It's not drawn properly. It's not drawn properly. Okay, so we have something like this, something like that. All right, it's not drawn properly, but that is how it is. Okay, all right, something like that. Of course, the maximum, we expect the maximum to be a higher point. Okay, which is this point here, and we have this point here which we've just drawn, this point which is 200, right, this point, and this point is 200. Okay, this is minus 200 pounds feet, and this one here we said is what did we say, this one is 153.38 pounds feet. All right, and then when you look at this region BC, the shear is 0, therefore you expect the slope for moment to be equal to 0. So for it to be 0, it will just be a straight line. So move from there to B up to so, something like this. Okay, and then of course we expect a close, but when you look at the direction of this moment is clockwise, okay, which is negative. But what we are going to look for is the value of the moment if we were to do a section just a little bit to the left of C. Okay, the moment that we are going to find there would be what? A positive one, and that is the internal moment in our structure, right? So that is the one that is doing the equilibrating. All right, so it's the one that is going to close up this part of the structure like so. Okay, so negative, so there we are saying minus 200, we are saying a minus 200 plus 200 equal to 0. So that is how it got closed up. All right, so let me rub this minus here because I have not been indicating that as the values I indicate inside. So this is negative, this is all negative, and this is positive. Okay, so this is positive, and then this is negative. All right, I think this is about it. This is really about it, and we are done. This is also 200 pounds feet, and so is 200 pounds feet, right? Then we have this value here, I mean this moment here is 0. We could find this distance here, right? But there is no need for now. We could find that value there. Okay, so I hope the video was helpful, and if it was, give me a thumbs up, like my video, and continue subscribing. Bye bye, and see you in my next screencast.